we'll have Ralph Blumenhagen on emergence of Calabi-Yau triple intersection numbers. So please.
Yeah, thank you, Gabriel, for the invitation to give this talk here in your online workshop. Yeah, so this is some work we did over the last maybe 2 or 3 years here in Munich, together with Niccolò Cribiori, who is now was a postdoc here and is now a postdoc in Leuven in Belgium, and 3 of my PhD students now. So there's an ongoing work, and it's related, or it's coming out of the so-called swampland program. And so today, essentially, I mean, the second part of the first part, I will give you a more general introduction into the topic and what we have done in these other papers here, the ones that you can see here. And the second part is essentially about the paper, the most recent paper with Alexander Glikovic that we published in June. And this is about this emergence of Calabi-Yau triple intersection numbers. Okay, here we are. Okay, so this emergence proposal is something that is, so to say, an additum to one of the famous swampland conjectures that people have proposed, in particular the swampland distance conjecture. So just a reminder, the swampland distance conjecture essentially says that if you approach a point that is infinitely far away in moduli space, then a tower of states becomes asymptotically light in an exponential way. And it was an observation by these people here that if you now take this tower and do, in essence, a field theory computation, integrating them out and computing corrections, one-loop corrections, for instance, to kinetic terms, you find the correct moduli dependence that is known from string theory. At least what the qualitatively dependence is concerned, but not necessarily the same numerical factor in front. So this made them make this proposal that I now state the proposal as it was published in a review article by Aaron Palti, that the dynamics, by which they meant the kinetic terms, for all fields are emergent in the infrared by integrating our towers of states down from an ultraviolet scale, which is below the Planck scale. So the sentence as it states, well, it's a bit up to interpretation, to be honest. So what we were asking ourselves is, so could this be a fundamental structure of quantum gravity? In the sense that effects, this in particular means that integrating out means that you do a loop computation, that things that we believe are tree level are in fact loop generated. This sounds strange, and we will come to that, how we could, so to say, reformulate this conjecture and make it a bit more precise. But maybe first, before I enter that, some heuristic reflection on emergence. So emergence, I'm just stating now something I read in this paper here, is an appearance of properties of a system that are novel with respect, no, I can't read it, to other more fundamental description of the same system. Okay, so it's nothing that we can obviously see from the first principles in which we formulate a theory that are, so to say, inherently in that system. So one has to get them in a more complicated way, I would say. So they're very indirectly contained in that. So more work is needed to extract that information. And give you an example, which is already pointing in the direction in which we want to go. So let's think about gravity and string theory. So string theory, we mostly have the perturbative description. So when the string coupling is small, and in this regime, as we know, the strings are the lightest objects, sense of their brains, d-brains, and so on are much heavier, parametrically heavier. And then when we quantize that system, the string, we know that the closed string in particular, that the graviton is there. So this is the massless excitation. And we also have the Polyakov action, which also explicitly contains the metric in this way. So here we would say, and when we now continue and compute, for instance, tree-level scattering amplitudes of these gravitons, we can reproduce essentially the Einstein-Hilbert term. No? So we get results that are consistent with an underlying Einstein-Hilbert term. So something like this, we would not call emergence. No? So this is something where gravity is there from the very beginning. I mean, you could, of course, say, well, gravity is emerging from the quantization of strings, but this is not what we mean here. In particular, there is a well-defined perturbative series, and there's a classical term, a tree-level scattering term, and this is what we call, this is definitely not a quantum effect. Okay, and this is also consistent with the computation we were first doing in this paper here, where we took this initial proposal and were applying the same integrating out procedure of this tower to an emergent string limit. And we were also seeing problems and terms appearing that we could not make any sense of, in particular logarithmic factors and so on. Okay, so, but of course, there are various infinite distance limits. This is just one of them, the perturbative string limit. So just imagine that there's another limit where, for instance, where we take the string coupling very large. And so this is usually what we call the M-theory limit. And in this limit, it's known that de Sitter branes are actually the lightest objects. So we would expect that the fundamental theory, in some sense, is not a theory of strings, it's a theory of de Sitter branes. In that sense, the quantization of de Sitter branes, which are just point particles, they do not have a graviton as an excitation. The only information they carry is their position. And if we put n of them on top of each other, I mean, this position is usually extended to a matrix. Yeah? And this already sounds very similar to the BFSS matrix model, which is a candidate for the description of M-theory in discrete light quantization and so on and so forth, which has this bosonic action here. And in this sense, I mean, for this model, we would definitely say that gravity is emerging. So first of all, I mean, it's just a matrix model. There is no metric here. There's no excitation of a graviton. But nevertheless, as when you read through the matrix model literature, so what's happening here is that if you look at the classical equations of motion of this matrix model, first of all, I mean, you do not have usually the interpretation of a large flat space-time. So this is just a special solution of the tree-level equations of motion, so that these matrices do commute, so that they are diagonal. And then if you then integrate out the off-diagonal pieces of these diagonal metrics, then you find the gravitational interactions at one loop. So this is very much what we have in mind when we talk about emergence, so that gravity, in fact, is just a loop effect, is a quantum effect. And here, so the first step, so to say, we have to go is to talk about space-time in the first place, so that space-time is emerging. And on top of that, it is a loop effect to induce the gravitational interactions on that flat space-time. So this is really what we have in mind. And here we would definitely say that gravity is an emergent concept. And behind that computation, as you know, is effectively the loop channel, tree channel equivalence of string theory. Yeah, so that one loop diagram of an open string can be interpreted as a tree-level exchange of a closed string, which is a carrier of the graviton. Okay, this is just heuristic so far. Now, let me see, to make this more precise, or to find more. I mean, this is already the proposal in which the direction in which we will make our proposal to refine the emergence proposal. But now let me go into a bit more detail and give more flesh to what I've been saying already. So first of all, so we have the, let me talk about the swampland distance conjecture and remind you. So as I said, in moduli space of quantum gravity, the moduli space of quantum gravity contains infinite distance limits where certain moduli fields go to infinity. And the measure on the moduli space tells you that this is infinite distance. Then Oguri-Waffer were proposing in 2006 that in such a limit, there's necessarily in quantum gravity a tower of states becoming exponentially light, where when we talk about all scales, we always keep the Planck scale fixed. So we are not decoupling gravity or so, because we want to have a theory of quantum gravity. So the Planck scale is the fixed quantity, yeah, and the dimension we are working in. And then you have a tower of states scaling in this exponential way. And familiar examples, I will come to that anyway, is the decoupling limit that we have already just seen. And for instance, decompactification limits. And the decoupling limit is the string tower of string excitations, which becomes asymptotically light. And in the decompactification limit, it will be the Kaluza-Klein modes, for instance. And the emergent string conjecture, which is a further refinement of the swampland distance conjecture by Lee, Lerche, and Weigand, tells you that these two kinds of limits are essentially all that can be in string theory or in quantum gravity. And they collected evidence for this picture. The second concept we need is the so-called species scale by Giadvali. And it claims that if we are in such a situation where we have many light states, the actual cutoff of quantum gravity is not the Planck scale anymore. It's a smaller scale, the one that he calls the species scale. So quantum effects will become already visible way below the Planck scale. And the relation, if n species is the number of light species, the formula that Gia was proposing or was deriving is that the species scale is given by Planck scale over this power of the number of species. Again, in the weakly coupled string limit, it will turn out that the species scale is nothing else than the very familiar string scale. Yeah? And in general, of course, the string scale is not the same as the Planck scale. There's a factor of GS square or something in between. And so in the perturbative limit, so MS will be smaller than M Planck. And in the extreme limit where the string coupling really goes to 0, MS will go to 0 if we keep M Planck fixed. And second, in this decompactification limits, where we say have a compactification and take a radius very large, the species scale will turn out to be, or turns out to be, the Planck scale of the higher dimensional theory. Yeah? This is all natural. And usually these two things are interpreted as limitations on the validity of an effective field theory one is working in. So say one is in a certain regime in parameter space and has derived an effective field theory, then of course, if you go further out in the moduli space and all these light states come in, or these exponentially light states come in, then you have to integrate them into your effective field theory. But infinitely many are, exponentially, since this is an exponentially large number of states coming in, this is something you cannot do in practice. Yeah. So the working assumption, or what we are also implicitly assuming here in the following, is that this is not just something as a limitation on the effective field theory, but they also reflect the structure of really full, what we call perturbative quantum gravity theories that arise in infinite distance limits in moduli space. So now we are going back, not only just talking about the effective field theory that we are working with to approximate our string theory, but really the full thing with all its massive excitations. So what do I mean by that? Just as an analogy to what we usually do in perturbative string theory. So in perturbative string theory, we have this small parameter GS. Here we have a large distance, but still we have a naturally small parameter, which is 1 over the distance. And this becomes small in that limit. And then we can still look at our, say, BPS spectra that we have in string theory, and we go to that limit. And how do they scale? How do they scale with this sort of coupling constants in terms of the species scale? If we compare all the towers that we have, all the states we have relative to the species scale, and look at how do they relatively scale with this coupling constants. And then we would call a light tower those towers of states that have a positive power of G alpha here, of G of the coupling constants. And a heavy tower, sort of a non-perturbative state is one where we have G in the denominator. Yeah. These things we would call the fundamental degrees of freedom of the perturbative quantum gravity theory that arises in this particular limit. And these things we would consider as classical solitonic-like objects or coherent states. And as we usually do, if we have a sort of a perturbative description, think of a path integral, when we integrate out something in loop diagrams, we are only integrating out the perturbative states. We are not integrating out the non-perturbative states. The non-perturbative states are bound states, so to say, coherent states of the fundamental degrees of freedom. And this picture, so to say, that is also valid in string theory, perturbative string theory, we now carry over to these two more general infinite distance limits. No? So this is sort of a prerequisite now for the application of the initial idea of the emergence proposal, which I again wrote here. So what we actually integrating out, so one could say that this was not very precise what they had in mind here, even though they might have had in mind what I'm saying now. So we only integrate out the full light towers in this infinite distance regime, but we also integrate out the full tower up to infinity, not just a finite number of these states, but like in string theory, where we also integrate or sum over all the string excitation up to infinity, we now integrate out all the full light towers in the infinite distance regime. So this is what we mean by integrating out. And what the light tower is, this is specified by the species scale, no? As I said, so towers that scale like this with respect to the species scale are light, and these guys here are heavy. So we integrate out the full towers of the states that are light in this sense. That's the proposal. So let's look at examples. So for the perturbative fundamental string, the light towers are the strings, string excitations. The mass scale is MS. String coupling is GS, is small. In general, this is accompanied by particle-like states of the same mass, the KK in winding modes. If we have compactification radii of order 1 and nothing parametrically larger. So the species scale in this case is the string scale. So it's like what we usually do if we now express all the other states that we have in terms of the species scale. Of course, the strings themselves, they scale like lambda tilde. And the D branes and the NS5 brane, for instance, they scale with some power of GS in the denominator. So for GS small, they are heavy and become infinitely heavy in the GS to 0 limit. These objects we usually describe from the string theory perspective as coherent states, boundary states, sometimes called for EP branes. And we are not integrating them out in our string theory loop diagrams, right? Okay, another example, and this is the one of interest here, is what we call the M-theory limit, or what is called the M-theory limit. This is a special decompactification limit. It's the strong coupling limit of type 2A, while keeping the lower dimensional Planck scale fixed. So you have to have a certain co-scaling such that the Planck scale is fixed. And in M-theory units, this means that, that you'll say linearly scale the size of the 11th direction, and at the same time co-scale the Planck scale in the 11th dimension and the internal radii in such a way that the radii, the size of the radii, the extra radii in units of the 11-dimensional Planck scale is kept fixed. You see when you multiply these two things, this factor drops out. But this co-scaling here guarantees that, for instance, here the tandem or the d-dimensional Planck scale is kept fixed. That's important to keep in mind. So all these limits are taken in this way. Okay, and if you now go through your, say, PPS spectra that we know are there and look at the lightest tower of states, you will find that it's not, maybe not unsurprisingly, that the D0 branes are the lightest states, and their mass, when expressed in terms, say, of the Planck scale in d dimensions, is like 1 over lambda. But when you now look at the induced species scale for this tower of D0 branes, you find that the species scale is the higher dimensional Planck scale. So it's the d+1 dimensional Planck scale in this case, which, by the way, the limit that we are taking scales in the same way with lambda as the 11th dimensional Planck scale. And moreover, you see, if you compare these two scales, that now the D0 branes are still lighter, parametrically lighter as the species scale. This is different. This is different than for the emergent string limit that we were discussing before. There, everything was of the order MS, both the excitations of the string and the species scale. So there, in principle, there is room for additional light towers that are sort of at threshold with the species scale. And indeed, if you go to the list, you find two of them, namely from the type 2A perspective, say the D2 brane and the NS5 brane. Their mass scale is also of the order of the species scale. So they should also be considered, they are threshold, and due to our recipe, they should still be considered as giving rise to light towers of states. So from M-theory perspective, these are nothing else than the transverse to the 11th direction, M2 branes and the transverse M5 branes. And this can give bound states with the D0 branes. So in other words, transverse M5 and M5 branes with KK momentum along the 11th direction. So in that particular scaling limit, these are the light towers of states. And for instance, longitudinal M2 branes would be heavy, would be like non-perturbative objects. Okay. So the proposal now is, or the refinement, if you want, is that in the infinite, so it's now the emergence proposal, I mean the M-theoretic version of it, in the infinite distance M-theory limit, so where we decompactify the 11th direction, with a Planck scale cap fixed, a perturbative quantum gravity theory arises whose low energy effective description emerges via quantum effects by integrating out the full infinite towers of states with a mass scale parametrically not larger than the 11th dimensional Planck scale. And the things that you have to integrate out are the things that I've just mentioned, transverse M2 and M5 branes. Okay, so one can claim many things. So is there any evidence for that? Well, there's an immediate problem. We don't know really what M-theory is. The only thing we have is this matrix model description. And there we saw that at least in this discrete light cone gauge, emergence is something that we would that is really happening. So gravity is induced by quantum effects. So the problem is that in general, if you want to prove or find evidence for that, it requires the quantization of M-theory. And moreover, gravity and space-time should emerge at the same time in one stroke, so to say. So it's not really clear how to do that. But there are certain couplings that we have control over. That's the nice thing. So the approach we were following it to collect evidence is to look at BPS saturated amplitudes, particular 1/2 BPS saturated amplitudes, because we know, even don't know we know what the microscopic VM theory is. We do know their BPS particles, their BPS states, and these are precisely the M2, M5 branes, and so on. So what we technically do, we will evaluate 1/2 BPS saturated one loop integrals. And as we will see, these will generally be not finite, this will be infinite. So we have to find a working regularization of the appearing UV divergences. And so to say, from the microscopic point of view, these amplitudes are something like, how should I say, it's still like an effective description that is, of course, only valid for these BPS protected quantities, because there we know that even though microscopically this might be a matrix model, but there should be bound states that are like M2 branes and M5 branes, and then we are integrating out these M2 branes and M5 branes to start with, so to say. Yeah. So this is something we can do, and then we can check whether we can get the full amplitude, the full, say, weakly coupled amplitude in string theory, the various contributions, just from a one loop computation, for instance. In particular, also the tree level term. So this is the thing we are doing. And
can I ask you a question here? But you probably will comment about it. What do you mean by working regularization as opposed to?
I will come to that.
Okay.
This is just the page that I wanted to show you. Okay. Working means it works, so it gives you the right result, but it's still an non-trivial statement. So recall a one loop diagram in string theory. That's helpful. And to be precise, so for instance, if you want to compute the R to the 4 term in string theory, and it's one loop correction. So the one loop correction, which is usually encoded in this parameter AD here, this is a 1/2 BPS protected quantity. So what you are integrating out is like a Schwinger type diagram, Schwinger like one loop diagram, where you only integrate out the 1/2 BPS states, and these are made from KK and winding modes satisfying the BPS condition. This is the BPS condition for winding and Kaluza-Klein modes. So you're integrating out over these modes. No string excitations. String excitations do not contribute. This is in type 2a, by the way. String excitations do not contribute. And in string theory, of course, we know how to do the integrating out procedure, because we integrate over the fundamental domain of the torus, and then we have this measure factor here. And of course, the fundamental domain, we cut out the actual singular contribution, which comes from 0. So because we are integrating out the fundamental domain, so we are missing, so to say, the dangerous portion. But you can go one step back. So here, this is a finite number. This is a finite moduli dependent quantity here. But now you can go one step back and look into your textbook, so the heuristic derivation of this result. And this is actually started with a real Schwinger-like integral. And you integrate now over particle-like states. You implement your BPS condition by hand. So in other words, you take this amplitude and you extend it to the full, not just the fundamental domain, again to the strip in the upper half plane, and then you carry out the integration over the real part, which does nothing else than implementing the BPS condition when you look back. So you could also start, or you would naively have started with integrating out particle-like states, okay, K and winding states, which is an infinite sum, and then a real-type Schwinger integral and the BPS condition implemented by this delta function. This thing per se is, of course, infinite, because you have not done the regularization you do in string theory. This is infinite, but you could now go ahead and try to regularize it. For instance, first of all, you have two sources now for the infinity here. First of all is this lower bound here, from the integral. So you could introduce a cut of epsilon here being very small, and then make an expansion in 1 over epsilon. Then you would see, okay, there's a divergence in 1 over epsilon, then there might be a constant term, and then things that vanish in the epsilon to 0 limit. And these divergences you just minimally subtract. Yeah, this is the working regularization I'm talking about. So you take this UV divergence and you regularize it by minimal subtraction. But then even after that, you still have to carry out these infinite sums here over the winding and KK modes. This could also be infinite, and they are. But in this particular case, you could easily regularize by zeta function regularization. And if you do this is in our paper, if you do this two-step procedure, naively compute this integral in this manner, you find the same result as the well-known string theory result. And this I call a working regularization. Yeah. So we have found a way to make this object, which is highly infinite, to give the same result as this one, as the exact result. And if we now integrate in M theory, the BPS states, particle-like states, we don't know how to do a loop computation in M theory from first principles, but we do know how to do real-type Schwinger integrals of particle-like states, which could be wrapped M2 branes or something. Yeah. So we are only having this result available. We are only having this expression available, and we are now looking very similar to what we have done here for the string diagram for such a regularization to make it finite. And so this we have done in these papers, in particular for the higher derivative R to the 4th term in theory with maximal supersymmetry. So type 2a on tori. And here's just a summary of what we found. So if you do, first of all, I mean, of course, this is not completely new, so there is a lot of previous work, but of course, these people have never looked into this from this swampland perspective and from the emergence proposal. So first of all, if you would do the computational perturbative string theory, you would start with your tree level result of that coupling, and you will find this result. Then you do your one loop computation, integrating out KK winding modes. Then you find a one loop thing, and these are virtual instantons here. And then you can also do, you can have also D-brane instanton contributions. So there will be an expansion like tree level, one loop, including also virtual instantons, and then D-brane instantons. And if this was well known before. So if you would now go ahead and integrate out, say, all the BPS states that you have in M theory. So you integrate out M2, M5, with KK momentum along the 11th direction. So these things you do integrate out in this particle-like Schwinger integral, implement the highly non-trivial BPS conditions here, do this, it's a longer computation, yeah, so do this regularization that I've described here, you will get a finite result, and when you then re-expand it in terms as for small gs, so which means for small radii, you will find precisely an expression like this, and you can essentially read off what each contribution is. And in particular, you will also find the tree level result from the perturbative picture. This is all contained in this one loop M theory-like Schwinger integral. Okay, our proposal now was, and what you're actually doing here is an Eisenstein series. Yeah? So this has been written like an Eisenstein series with some U-duality groups and some representation and some level and so on. Not so important here. But of course, if you just define it like this, I mean, this thing is still divergent and you have to regularize it. The thing that we were proposing is how, for instance, microscopically you could regularize this expression, not using analytic continuation, what mathematicians usually, of course, like to do. Okay, so this is so to say, if you integrate out everything, then you are sort of in the middle. No? So you don't have a distinction between light and heavy modes. Sorry, you don't have a distinction between light and heavy modes, so you just integrate everything there is. So this computation you could think of is valid in the desert. Desert means for GS being of order 1. Yeah, so neither in the weakly nor in the strongly coupled case from the type 2A. Our proposal was that there's another infinite distance limit where GS goes very large. So then you are in what we call the perturbative M-theory regime. So the 11th circle is very big, and you should only integrate out the transverse M2 and M5 branes now carrying KK momentum. So less states than you have here. And you can do that. And you find precisely this expression. So notice there's a slightly smaller U-duality group now here, because you are kicking out some of the states that fill out the full representation here. There's a slightly different representation here. And this one is precisely the KK mode along the 11th direction. And by our proposal, these two expressions here should be the same after all. Now we are computing a BPS protected quantity. So wherever we compute it, it should be the same. And for the first dimensions, for the large dimension, we were showing explicitly that they are indeed the same. So that there is some redundancy in this expression, things that cancel precisely in the way that eventually it can be expressed in this shorter way. So this is the physics here. No? So this is highly non-trivial, and this is why we believe that we have a working regularization here. So you don't need, so this is sort of, so this is what the emergence proposal would tell you, so that the full result here even is a quantum effect in M theory, and this prerequisite, what I mentioned, that we are only in the perturbative regime, infinite distance limits, only the light states are integrated out, heavy states are instantons. So that this equality here, so to say, is a proof or is a sign of the correctness of our proposal. No? Only integrating out light modes. Okay, so we did this also for the F to the 4 term with Manuel Atime and Antonia Pares-Gevopolo. In a theory with 16 supercharges only, so we're considering type 2A on K3, and there's a heteroic dual even here. There are also previous results, and we're doing very similar analysis, and we find very similar results. So again, you get the full quantum, you get the full expansion for GS small just by a loop diagram. And you're computing a F to the 4, so a gauge coupling, just by computing the integral over all potential BPS states. And then we restrict to the ones that are light in the strongly coupled regime. We find a different thing, but it turns out that there are redundancies in this expression so that the two things are equal at the end. Okay, so far, so good. So working regularization for R to the 4, F to the 4, with a lot of supersymmetry that worked well. And there was no need, there was no tree-level term. This is important. There's no tree-level term in the M theory, in the strongly coupled or even in the desert here. So there's no what we call M theory. So the one loop thing computation gives you the full exact result from the weakly coupled perspective. Okay, so then the question is, so since the emergence proposal was about kinetic terms, at that time they had more the kinetic terms in mind. And here we were discussing higher order effects. So can we do a similar computation for kinetic terms? So we need a 1/2 BPS protected object that encodes information about kinetic terms, and that indeed exists if we now compactify type 2A on a Calabi-Yau, breaking even now 1/4 of supersymmetry, so ending up with 8 supercharges, so n equal 2 supersymmetry in 4 dimensions. And here, now we are talking about the vector multiplied moduli space, and we would like to go to infinite distance limits in the vector multiplied moduli space. And the object of interest is the so-called prepotential. This is 1/2 BPS protected. And in the weakly coupled regime, we know that it enjoys an expansion like this. So there is again a tree-level term, which is given by the triple intersection numbers. T are the Kähler moduli. I don't know whether I have to explain all that. So T are the Kähler moduli. Then there's this effect here. And then we have the non-perturbative effects from worldsheet instantons, where we sum over essentially the homology lattice of 2 cycles. And these degeneration factors here are the so-called Gopakuma-Waffer invariants, if you express it in terms of the 3 here. So these are things that are hard to get. I mean, of course, you cannot count all of these things by hand. It's also an index. But mirror symmetry is very, very powerful. In these cases, via mirror symmetry, one can determine these Gopakuma-Waffer invariants by a classical computation of periods and so on the type 2b side. But what we are now interested in particular is this object here. So it's the what we would call the tree level term from the weakly coupled perspective. So can we get that from a loop computation in the strongly coupled regime in M theory? And this, what the rest of the talk will be is speculative, but it will make a proposal of how to define, now in this case, it will be much more complicated, a working regularization, okay? More we cannot hope for because we don't have the microscopic description of M theory. Again, we can only hope to write a BPS protected integral, which was already done by Gopakuma-Waffer, and then find a working regularization of the expression. Okay, so Gopakuma-Waffer indeed did a lot of work already. So they were precisely considering the M theory limit. And then instead of having Worldsheet instantons and so on, they were integrating out bound states of D2 and D0 branes, D2 branes wrapping 2 cycles on the Calabi-Yau. And they came up with this expression for the prepotential, valid in the strongly coupled regime. You see, this is not an integral over strings or whatever. It's really an integral over the D branes, no? Over the light, precisely over the light species that we were just arguing to be the light things in the M theory limit, bound states of D2 and D0. Okay, so you see here is the central charge. So it looks very much like a real Schwinger integral, and indeed it is. And if you now do the computation, and it's easier not directly to look at F0 here, but just take the third derivative, and now we are heading for this triple intersection number here, because then you can explicitly carry out that integral. So if you, for instance, if you choose H11 equal 1, so if you now compute the third derivative of F0, but by this I mean this expression here of the Gopakuma-Waffer expression, you can explicitly do the integral and you find the following expression. So you get a sum over the Gopakuma-Waffer invariance from the third derivative homology vector third. First of all, then you get these terms here. These are the terms that were considered by Gopakuma-Waffer. And in the weakly coupled regime, these terms are precisely the ones that give you this factor. So if you integrate out that expression that I was just showing you 3 times, you find the polylogarithm here. So, but there's another term. There's this offset by 1/2. Yeah. So, and of course, this is the candidate for giving the contribution that we were looking for here. Yeah. Okay. So, but of course, you still have the sum here over all Gopakuma-Waffer invariants. So, for our claim to be correct, we need a regularization of this sum here, so of this term, such that this gives the triple intersection numbers. So that's the proposal. So emergence in this case would tell you that it should better be that this combination here with this factor 1/2 gives you the triple intersection number to find a regularization. That's the problem, because these Gopakuma-Waffer invariants in general, they are known to grow exponentially. So this is much more than just doing a zeta function regularization or so. So this really means that you have to regularize a sum over an exponentially growing factor here. Okay, so how did we proceed? So the rest of the talk is essentially how we did it, or give you an idea of how we did it. Okay, so you get some intuition by looking at the regularization you usually do, or which you can do for zeta function regularization. So say you want to define the sum over all integers, or so positive integers, to some, say, odd power 2n minus 1. Yeah. So what you do in practice, what you could do is, so first of all, you make this a double sum by introducing sort of an empty sum over L1 to infinity of 1, and zeta function regularize it, which is minus 1/2 here. So then you get this expression. Yeah. Yeah, and introduce also this right, and also introduce here this regulator. So lambda essentially is the regulator here. So lambda we send in the end to infinity. So then the q becomes 1. So if q is 1, then this term is not there, and you have the same expression as here. You have an empty sum over L, but this is minus 1/2, and this kills this factor minus 2 here. Okay, so this is the regulator here. But now if you look carefully, you see that you can write this double sum here as the sum over all the divisors of m to the power 2n minus 1. So this is a well-known expression here. And the remaining thing you are summing over is the combination k times L times k. So this is sum over all divisors of m, sorry. And now you realize that this sum here you can write as part of an Eisenstein series. So the Eisenstein series e to the 2n has precisely this combination here, as you can see. There's a prefactor like this, which you usually write as 2 over some zeta function. But of course, without the minus 1, without that factor. So we explicitly have to subtract the factor 1 here in order to make this here an identity. But now, since this is an Eisenstein series has nice modular properties. We send lambda to infinity, so we can apply here a modular S transformation to this term here. And if we do this, so it's again e2, and so it's tau to the factor 2n, I think, and then e2n of tau, if tau is I over lambda. Yeah, and if you look at what you get, is you then find from this modular form, you get terms that are you get one term that is divergent, and the rest are only terms that are vanishing. So there is no constant term in here. You only get divergence and vanishing terms. So again, so now we minimally subtract this divergence here, and then take the limit. From here, you don't get anything from the Eisenstein series because there was no constant term. So the only contribution that you get is coming from this factor minus 1 here. Yeah. So you get precisely this here, and this is what we want. So this is zeta of 1 minus 2n. This is not the only way to regularize this sum, I should say. It's one way, but it's the way that we will use in the following, essentially. So this gives you an idea of what we are doing. Yeah. Okay, so the aim now is to generalize this procedure to 0.2 Carver couplings. Okay, so before we do that, or maybe should I skip that? How much time do I have? I have 15 minutes, no? Gabriel?
Well, you have about, you have an hour in total, so you still have about 15 minutes, yeah, 18 minutes, 17 minutes,
okay, yeah, maybe
70 minutes.
I don't go through. Okay, so I don't want to confuse you too much. So instead of looking at this M-theory limit, in the first place, we do something simpler. So we take a different limit, not the M-theory limit. We take this Calabi-Yau with these Hodge numbers and take another limit now, a decompactification limit to 60. Again, in this way, it's a co-scaled limit. 4-dimensional Planck scale is constant. In this limit, you can again make this analysis. What are the light states? What you should integrate out in a Schwinger-like integral. And here it's only the D2 branes wrapping the elliptic fiber. This is an elliptically fibered Calabi-Yau. And here it turns out, this is why we have arranged this limit, that only D2 branes wrapping the elliptic fiber are among the light towers of states. So now we would only like to integrate out this, so to say, subtower. Only this D2 branes wrapping the elliptic fiber. What would their contribution to the prepotential be? It's not the full prepotential. This we cannot expect. It will be part of it. But this computation can be easily done because this designs like that. The Gopa-Kumar-Waffa invariance in that sector, so of branes wrapping only the fiber, is constant. Does not depend on N1. Does not depend on the homology class. It's always 540. It's always 2 times chi or minus chi. Yeah. So integrating in this case out this tower of D2 and D0 branes would give you the following expressions, the same expression that we had before. I only introduced here the constant Gopa-Kumar-Waffa invariance. But here we have really a zeta function regularization. So here, this is why we're doing this. Here, we can simply zeta function regularize this expression here. So we will get 270 zeta minus 3. This is 9/4. And the rest again is 9/4 times E4. I mean, this part here, except for the constant term. So what I'm saying is if I regularize this first term, which is formally infinite, I get the full E4 modular Eisenstein series. Okay, so this tells you that this factor here, and also the 1/2 and the zeta function, was precisely correct to make the expression modular invariant, or modular covariant if you want. So this gives you another hint that this factor 1/2 here, if appropriately regularized, has a physical meaning. Yeah? So it really completes it to E4. So, but what we have effectively done here is, what you could see is, so the regularization we did, remember our previous slides, this is precisely the regular. So if you expand this quotient here, make the denominator into a geometric series, you can write this expression like here, yeah. And this is precisely our proposed regularization from a few slides back. So this expression was appearing in the regularization of the zeta function. So the lesson we can see here is that the exponential terms in the Yukawa couplings can serve as a regularization of the 0-point Yukawa coupling. Yeah. So here it seems to be not more than a consistency check, but precisely this idea will be useful in a moment. If we namely look at now the M-theory limit, the actual case of interest. Yeah. So now we are really taking the limit that I mentioned at the very beginning, the M-theory limit. This is this co-scaling that we are doing. And now, if emergence is correct, all triple intersection numbers should arise from a regularization of the what we call the 0-point Yukawa couplings. So let's discuss this for Calabi-Yau with 1 Kähler modulus. So we would define the 0-point Yukawa coupling like here. So we take the limit. So we think that we should take the limit. So, okay, Q is e to the minus, I didn't mention this yet. So Q is e to the minus tau, t, sorry, or 2 pi t. So we consider this as a regularization of this factor 1/2 and this constant. So we take this as a we take this piece as a regularization of that piece. We do the same here. Yeah, so this is our regularization, and then we subtract the divergences. So this would be a regularized version. There are two problems now. I mean, first of all, well, they are related. These Kopakuma-Waffer invariants, as I mentioned, grow exponentially. They are not constant like before, 440. And moreover, due to this exponential growth, we know already that in many cases, we cannot take the limit t to 0 because t to 0 is not in the moduli space anymore. So there are quantum corrections to the Calabi-Yau moduli space that move the former classical t to 0 point to a finite distance. Yeah? So this is not in the moduli space, so we have to deal with that problem. But we know that these Calabi-Yau manifolds with 1 Kähler modulus, they have a conifold singularity at this finite number Tc. So this is really the quantum corrected origin. Yeah, this is the quantum correction to what we call the origin in the gauge linear sigma model, which is formally the t to 0 point here, yeah. Here's a singularity. Here's something that is divergent. So it's natural not to take now the limit to 0, but to take the limit to this quantum corrected 0, yeah, which means to the conifold point. Okay, so now, in order to do this, of course, you need to know these numbers that we don't know. I mean, because we are not a Calabi-Yau daemon who can count all these numbers, count these curves. But we know that if we have mirror symmetry in place and we have a Calabi-Yau where we know the mirror dual and know the periods and everything, whatever we count, the Calabi-Yau daemon will count, has to be the same result as the one we get from mirror symmetry. So for this expression here, yeah, we will get what we would call the weakly coupled expression from mirror symmetry. But again, this term does not contain kappa TTT. Yeah? Because this is precisely the analog of this factor, where is it? Of this factor -1 here that I wrote here. It does not contain that precise thing. If we write it in this way, and enforce it, that we express it in terms of the third derivative of the prepotential, we have by hand to subtract kappa TTT. Then this side is equal to that side. And then we minimally subtract the divergences, but not taking the limit to infinity or to 0, but to the conifold locus. This is the non-trivial part here. Okay, so now it's clear. So at least we have a prescription. This is not a proposal. This is the proposed regularization of the 0-point Yukawa coupling. But we evaluate this expression. And it's important to notice that we are taking here the limit to the conifold locus. And moreover, it's also important to notice that explicitly the desired result, which is kappa TTT, already appears, of course, here as a correction that we had to do by hand. Yeah, just in order that this side, we are not cheating. I wanted to say we are not cheating. We just make sure that this piece here is literally the one that we compute for mirror symmetry, minus KTT. So we have already the result in place. Here's a minus, there's a minus, as long as the limit T to TC of the weakly coupled prepotential here, third derivative, is only giving divergent and vanishing terms. Divergent and vanishing terms, like in this toy example I was showing you. The divergences we minimal subtract. If there's no other constant coming in, then this limit will give you KTT. So this is something we can check. We have to evaluate this expression. What is the problem? Now, the problem is that if you start, say, with the periods in the large complex structure regime or large radius regime, the conifold point is usually at the boundary of convergence of that expression. So that we cannot so easily take that limit. We need infinitely many terms. And moreover, one cannot simply apply a modular transformation. Modular transformation do not play any role here to get the behavior close to TC. So we have to go one step back. So first of all, we have to determine the periods not close to the infinite distance point, but close to the conifold points by solving the Picard-Fuchs equations. Then we have to determine a symplectic basis and glue them continuously to the large complex structure chart. And then we can take the limit, T to TC. So in doing this computation, which were mostly done by my student, and he was also supported by communication with these three people here. No, it's four people, Alvarez Garcia, Machlar, Key, and Rühle. And so they will describe precisely how to do this more generally in an upcoming paper. Okay, let's look at the quintic. Maybe most of you know something about it. So for the quintic, we have the mirror quintic. So that's the mirror quintic. So it's the Z5 orbifold of the original quintic. And the conifold locus, so there's only one complex structure modulus, which is mirror dual to the one Kähler modulus that we have. And the conifold point is at psi equal 1 in these coordinates. Now, first of all, now one has to solve the Picard-Fuchs equation close to the conifold singularity and glue them to the large complex structure regime in a continuous manner. And if you have done that, you will find that your periods can be expressed in terms of this parameter here, which is now the one that goes to 0 at the conifold locus in this way. So this is the usual behavior you expect for approaching a conifold singularity. It has the right monodromy when you go once around it. And these functions, rho, the details are not important. I mean, these are just series in U, infinite series in U, starting with a constant. And when they are not starting with a constant, but linearly, we explicitly write it like here and here. Then you can compute the Kähler modulus, which is the ratio of two of the periods in this way. And then you see that T goes to TC when U goes to 0. So at the conifold locus, T goes to TC as wanted. So you can use this expression now for the Yukawa coupling. And sorry, you can now use the following expression already from the old Candela's De Losa paper. And when you for the Yukawa coupling of the mirror dual quintic, so this is given in terms like this, in terms of the complex structure moduli. This is also a complex structure modulus coefficient. So if you insert everything back in, if you insert everything, this information into our expression, you find that the third derivative of the weakly coupled prepotential has an expansion of this form with many log factors and U factors. But if you order them according to their power, you find that there are divergent terms like this one. So for u going to 0, this diverges and many more. Then there are vanishing terms. There could in principle be a constant term, but there is none. So the constant term really vanishes. So if you now go back to this expression here and take the limit, you get no contribution from here. You only get the divergences you subtract, and you only get this contribution, and that's the one that we want to have. So this prescription, this sort of working regularization, gives you indeed the desired result. So this is what we wanted. So it works well for all, or we expect to work it very similarly for all other 14 Calabi-Yaos, known Calabi-Yaos with H11 equal 1. We have in the paper, we have analyzed also 2 Calabi-Yaos with 2 Kähler moduli, like this one, the elliptic vibration we had, and another that's a K3 vibration. Of course, here many new questions appear, which are not completely resolved yet. So they have a much more involved singularity structure first. So there you get 2 singularities in principle. So for instance, for this one, you will find 2 conifold singularities. These are the 2 curves that I'm drawing here. But they do not intersect into a single point, but they do intersect in 3 points, where one is also singular, which you have to resolve in this fashion. And then the question is, okay, so to which point, complex Coulomb-dimension 2 point, do I have to take the limit? So what is playing the role of the conifold point for these more general Calabi-Yaos? If we have 2 intersecting conifold loci, like this is happening for this thing, then it turned out, we didn't do the full analysis, but we were showing that if we take this point here, the most natural one, so to say, this already works. So we could still do the limit, we could compute the periods around this singular point here, and then take the limit and see that there's no constant arising here. Either it's vanishing or it's divergent. This case was a bit more complicated. There we only were successful in taking a limit to one of these resolved points here. But now what we are now doing in the moment is to do a much more systematic analysis. So the upshot is we have following the same procedure more or less as we did for the R to the 4 and F to the 4 terms, where we could zeta function regularization. We extended, so to say, this regularization to the expressions that appear for n equal 2 supersymmetry in 4 dimensions for the prepotential or its third derivative, with the difficulty of having this exponentially growing Gopa-Kuma-Waffa invariance. For Calabi-Yau manifolds with 1 Kähler moduli, the prescription worked well. We have a nice regularization of that. For more than 1 Kähler modulus, more work is needed, I would say, to get the full picture or the information to which point we have to do it. So which are the good singularities, so to say. This is what we are working on in the moment. And so I come to my conclusions now. So we provided evidence for the M-theoretic emergence also of kinetic terms, not just higher order terms in 4D n equal 2 vacua. So remember that from the weakly coupled point of view, type 2a, the origin of these kinetic terms is in the 10-dimensional Einstein-Hilbert term. So we proposed a pragmatic working regularization of the Gopa-Kuma-Waffa loop integral. And we pointed out that there's a nice, as our regularization procedure was showing, there's a nice relation to singularities in the Calabi-Yau moduli space. So if everything would work out fine, one could say the following. So the Calabi-Yau geometry, in particular the geometry on the moduli space, knows about quantum gravity. So it encodes the emergent string conjecture. This is this famous work by Lee, Lerche, and Weigand. It encodes the emergent string conjecture for infinite distance points. And it seems to encode, be careful here, emergence via its singular loci. So large complex structures, singular loci, both have their meaning, have their role, so to say. For string, they know a lot about string theory, even though they are just Calabi-Yau geometries. They seem to know a lot about string theory. Of course, the actual goal would be a generalization to non-BPS amplitudes. As I told you, these BPS amplitudes are still sort of effective description of something for which we don't know the microscopic description. For instance, the 10-dimensional kinetic term itself, this is not BPS protected. in 10D now. So we don't know how to get the Einstein-Hilbert term, for instance, from an M-theory computation directly. So this requires the quantization of M-theory. There was a proposal by Hattab and Pardee, also working in these directions in relation to effective Fermi gas description. And moreover, the whole thing that we are proposing here, of course, is already, we have already an example where it's realized, and this is the BFSS matrix model. But it's, of course, in a discrete light congage, you always do finite n computations and so on and so forth. But there, it's definitely the case that you have to do, in the matrix model, you have to do a one-loop computation to get the leading order term in the graviton, for the graviton scattering amplitude that scales like velocity to the fourth power over the impact parameter, or the distance r to the 7. So what's happening here, by the way, is that this velocity breaks supersymmetry. Now, so with no velocity, of course, the potential is 0 because we have maximal supersymmetry. So only when the particles, the gravitons have relative velocity, break supersymmetry, then you get a non-vanishing potential. But of course, how matrix theory enters here is not so clear. I mean, the matrix model limit that one usually takes, the Seiberg limit, is different, at first sight, different from the isotropic M-theory limit that we are taking. But of course, it's not excluded that they are dual, but we don't know at the moment. This is something we don't know. Of course, the actual goal is sort of to learn something from this swampland approach here. We are now coming, so to say, with new questions from a new angle, maybe eventually to learn something about the ultimate goal, which is the formulation of M-theory. So this is all I want to say. I have no slide with thank you, so I say thank you.
Thanks very much, Ralph. Very nice talk. Thank you. Thanks.
Yes, welcome.
Are there any questions?